Threads are very useful kernel artifact that allows the application to spin up another body of execution and execute certain code so that you can take advantage of multiple cores if you have one, or if your single process is too overloaded. Right? And there are very nicely logical tasks that you can be broken into multiple threads, and those can be executed. While the threads, on the other hand, come with, extreme complexity, especially with race conditions, shared state, transfer state, and managing mutexes and locks, right, between those threads. This is where threads are never fun. And there was a whole paper about the evils of thread. Well, that paper is a little bit old. Now, threading libraries have been enhanced to solve most of the problem in that paper, but still, challenges still exist when it comes to threading. So today, I want to talk about when to use thread. When are the appropriate use cases where you said, oh, that kind of nice would be to use threads. And I'll focus specifically on the backend here because that's the specialty of this channel. There are cases, of course, where you can use the threads in the client, in the front end, but that's out of the scope of this particular video. Let's jump into it. So before we start, let's quickly describe the difference between a process and a thread. You see, a process is I call a process as a program in motion. That is the compiled program that you compiled. You get an executable file, exe, or a binary file in Linux. And that's the program. It's a file. It's static, lives there, doesn't move. But once you double click it in Windows, that is, you spin up and you process out of this program, you get a live, a live program with personality, and moods and things like that. The process can get angry, it can get sad. Yes, they do, right? Why do you think processes crash? Because they're, anxious. That's why they crash. So what happens is when you spin up a process, you get a little bit of new things that describes this aliveness of this process, becomes alive. So it has a heap where you store memory and a large object. You have a stack where functions frames can be, called, and variables, local variables can be defined. And that's what basically describes this. You have a whole, process control block that tells you, oh, this is where the current execution is. This is where the pointer of the program is executing, right? And many other things, right, that the process has. So when you essentially spin up another process, i.e. you double click the same program again, you get a completely different process that has nothing to do with the first process. It has its own stack, it has its own memory, has its own virtual addressing space, not shared at all with the original one, right? It has its own process control block, has its own registers, coding section. Although the code is technically identical, they are in different memory location. Now, virtually behind the scenes, the kernel and the operating system is smart. They link those two code pieces to the same physical memory so that we don't give multiple copy of the same code, right? But the heap and the stack are all different locations. So that's what the process is. When you spin up a thread, on the other hand, a thread is a lightweight process, i.e. it shares everything with the parent process that spins it up. But it does have only the things that absolutely require for execution. So it shares the entire virtual memory space. So as a thread, you technically have access to the entire virtual memory space of your parent process. That's why people say threads are dangerous as a result, right? And you, as a thread, also have the heap is shared with the parent process, right? The code is shared with the parent process. That is identical. Like we're talking the same virtual memory space. Everything is identical, right? So also the execution in this particular hand, that's the only difference. That's because the threads has a thread control block, which has these registers that says, oh, because technically the thread and the process can be can be in different position in their execution, right? And that's where you need a new set of registers just for those threads, like the program counter, for example. Right? So the thread needs a new program counter that say, oh, I'm executing printf. Oh, I'm actually executing this 1 + 1. Oh, I'm executing n + 1, something like that. Well, the process can do completely something else, right? That's why threads can also be scheduled on a process as a different thing completely, right? But the benefits are they share these things with memory. So that's a thread. People usually use threads because they are lighter weight. That's when we talk about threads and using thread, because they are lighter weight as a result. And there is also benefit between context switching. When you context switch between a thread and another thread in the same process, it's way cheaper than context switching a process to another process that are different. Even if they are technically the same program, it's also a higher cost to that switching, just because of the sheer amount of not shareability. Right? There are things that are shareable. The CPU can leave the things that has been cached in the L caches and not flush them. But if you switch between processes, you'll need it. So that was like a brief introduction between the difference between a process and a thread. It's really its own video, but in general. But when do you use a thread? That's the question that we need to answer. Let's not get out sidetracked. If you're interested to learn more, check out my Fundamentals of Operating System course right there, oscourse.win. Okay, that will redirect you to the latest coupon on Udemy. So with that out of the way, what are the use cases where we can use threads, now that we understood all of that? Okay, so the first use case that you can use threading for effectively is when you have a task that is essentially causes a blocking IO, right? What is a task? A task is basically, to me, it's a logical unit of work that is a collection of instructions. That's what a task is, right? So one process can execute many tasks, and you can logically divide your task accordingly, right? It's just a naming convention for us, right? So you're about to, I don't know, read from disk, write to a log, that's a task. Send a request, that's a task, right? Makes sense? Process this read request, go read index.html from this, that's a task, right? So blocking IO is when you read from disk, effectively only from disk, like you're doing a file IO read or write, and essentially using non-asynchronous interfaces in the kernel, right? Pretty much everything is blocking in the kernel when it comes to file IO. When you do a read to a file, the kernel will put your process into a blocked state, right? And as a result, the operating system scheduler, which is another component, will look at your process. Oh, it's blocked. You're waiting. Let's kick you out and get someone who is actually have precious instructions to execute. Because at the end of the day, all these processes and threads, they're fighting for the CPU. They all have instructions to execute on the CPU, right? There are, of course, other resource and commodity like IO and disk and bandwidth, but the most important one is the CPU. So they're all fighting for this time. So if you're not doing anything, you're just sitting there blocked, someone else can use your core, even if there are many cores, right? And the moment you do switch, context switch, there is a cost associated with that. You're flushing everything that is in the cache, right? Especially the virtual memory mappings, TLB, things like that. So there is a cost associated with that, which can slow down things, which means if you ever became available again, you need to switch you back in the processor, one of the cores, so you can resume execution, which can be a little bit expensive. We're talking 200, 300 nanoseconds, not much. Depends on how many writes have been performed to memory and all that stuff. But essentially, that is it, right? So the exception here, if you use IOU ring, right? IOU ring is an asynchronous interface that allows you to perform file operations on non-blocking file operations, right? Without blocking the client. Now I keep saying file because socket IO by design 20 years ago we solved this blocking issue with socket. It used to be a problem, right? Back way 20 years ago, even a little bit more, right? Where if you have a socket, like you have connections and you have one connection from a client and your backend calls read, hey, I want to see if someone send me something on this connection, if the client send me data on this connection. So you call read and you will be blocked because, well, the client didn't send anything. So you'll stay there blocked until the client actually send data, which is so weird, right? This will halt the backend completely. So they solved this problem way back ago, right? With many interfaces. One of them is select, another one is epoll, right? And I talk about this in details in my fundamentals of operating system. If you're interested, check it out. It's right here, oscourse.win, oscourse.win. So yeah, so epoll allows you to do socket IO asynchronously. So that is non-blocking, right? So you can safely do that. So that's not where you use threads. You don't use threads essentially to read from sockets. We can use it, but you don't have to. Does that make sense? It's not going to block you, right? We're going to talk about that in a minute. There are cases where, well, you can even use threads, but you don't have to because it's not blocking you per se, right? So that's the first thing. If you're ever blocked in a situation where you're blocked, then probably just spin up a new thread or use a thread pool. Like spin up existing threads, 5, 10, whatever the number is. Usually this number is matched to your logical cores, i.e. if you have a hyper-threading enables, that is basically the number of physical cores times 2. So you have 4 cores, that is 8 usually. So you spin up 8, and that's your thread pool. And you just go with 8, right? Assuming 1 thread per core. Well, that's just, it's just a number at the end of the day. A lot of complex stuff happen at that level, right? And you can a little bit put more load if you want to. So then let's get an example. What example of this? An example of this is when you do logging, right? Part of your request, right? You let's say you have a backend and it receives a request, right? And part of the request is to do, like, you want to process this request in the same process. Let's say you're a single process, no threads, nothing. And you take the request and you write that, hey, I received this request. You write it to disk, right? That write, 99% of the time it's blocking. You might not feel it, of course, because it takes 500 microseconds, right? And depends on your SSD, and depends on the page cache, it depends on the operating system file cache, it depends on so many things. But you won't feel it. But if it happens a million times, in a very short period of time, you will start seeing it, that your process is being blocked and unblocked and blocked and unblocked. And you can see the state. It's called the wait state in top command, right? Or also in the task manager in Windows. You can see that, oh, my process has been in blocked state or wait state for like 40% of the time, right? Or 30% of the time, something like that. And I think I made a video about that where I just basically spin up like a Postgres client, and I made like an infinite insert. Like this app just completely just does a bunch of insert, and I put the Postgres client and database in the same thing on the same the same machine. And you see the CPU is just waiting because insert is just a bunch of writes. We barely do any CPU. So the Postgres and process, the backend process as they call it in Postgres, it's just there blocked and wait. It's wait because most of the stuff is doing IO. It's writing to disk, right? So most of the time it's just being waiting. So this state, it would be beneficial if you spin up another process or another thread and let that thread be the blocked one, right? So you're gonna still see blocked in this particular case, but it's another thread. Why? Because now the main process can be free to execute other stuff. You might say, what other stuff? Well, accept another request, right? Or respond to something else before. And that's where you as a programmer come into the picture to understand what you are doing right here. And as a result, you just shuffle things around, shuffle tasks around so that you can benefit of this asynchronicity, right? Because the moment you spin another thread to do other tasks, that's an asynchronous behavior, right? You just like, boop, you go ahead and write the log and let me know when you're done, right? And you basically have all of these writers as processes, and Postgres does that as well, right? As a database, it has like wall writers, it has auto vacuum workers, processes, so that it doesn't be blocked with all these operations. So that's one use case, right? Another, the same within the same thing here, Node. If you use Node.js, you will know that Node.js use a library called libuv, right? Which actually is an asynchronous interface that allows you, it's just a wrapper on top of the operating system that allows you as a client to not worry about asynchronous stuff, right? So you just say, hey, read me this file, and it will become an asynchronous non-blocking. That's why Node.js, I don't know if they still do it, like they say like, we are asynchronous non-blocking, what do they call it? Framework? Runtime, JavaScript runtime, right? And Bun as well, the same thing, right? And that's because they can read from disk without being blocked. And the reason they do it is because they use this library, which does exactly the same thing we just discussed. They have a thread pool, and you can configure this thread pool UV, and you say, hey, file read goes there. If you want to block, you go through the thread pool. If you want to do a socket IO read or accept, you go through epool. Or if you're Windows, because epool is a Linux thing, right? If you're Windows, you go through the IO completionist ports, I think that's what it's called, right? So there is like all these interfaces with all different kernels. Like even Mac has different things. KQ, I think that's what's called. But yeah, so you can see this avoiding blocking operation is important. The second reason why you might need threads is if the task is you're about to execute is very CPU intensive, and you have other, more frequent tasks that you need to execute. An example is basically you're building a backend that has an API, right? And this API is, let's say, CPU intensive. Like, give me an example. Does sorting for some reason. You're sorting some results, right? On the client side. I don't know why you would do it. Usually sorting, if you're reading something from the database, you sort it right there and then. But again, sorting is a very CPU intensive operation, right? It keeps switching stuff. So any task like that, right? So you can right then and then when you receive a request, like even in Node or Bun, you can just write your code right there to execute, which most people do, right? If you do that, then that main thread, main process is executing your request. And I'm not saying that is wrong, but if your request has a loop and it does a lot of CPU intensive instructions, and you're waiting for more clients to come in, right? And you need to finish your loop to go to the next one, right? You won't be able to move on to the next request and help accept connections, help read requests, help process other requests if you're busy executing this very CPU intensive task. So in that particular case, it will be useful to spin up a pool of threads or just a thread, right? And usually, yeah, you will have a thread pool, right? A thread pool is useful because it's already there, hot, and you can just delegate a task for existing thread, as opposed you don't want to spin up a thread for every request. That's just mad, right? Madness. That will just because the cost of spinning threads can also take time, right? So you just make them hot there and let them execute the stuff. So So you would do that, and then you would execute the CPU intensive workload in an existing thread or in a new thread, while your existing process can do what? Can just move on to do other things, right? Hey, let me move on and read another request. And this pattern, you see it common with queues, right? So you would, for example, the way you would do it is you would set up a queue like RabbitMQ or Kafka. Kafka a little bit too much for the job here, but like a simple queue. Take a simple queue, like very, very, very simple queue that's just does queue. Doesn't have any fancy features like that, right? So what you would do is you would the main process will accept the request. It will read the request, understand it, and they will just throw that request into as a message in the queue, and then just move on. And then the thread pool will be smart enough to pick up a job from the queue and then start executing it. And then, of course, there should be messaging between the thread and the process to say, hey, I picked up this job and now it's done. And now you can of course embed all of this system with some sort of a feedback mechanism that hey client, I received the request, I didn't execute it yet, here's a handle, here's an ID for your request, check back later on me, I'll let you know when it's done, right? That's another common approach. You can do that, and you can basically block the client and never respond until the one of those threads actually receives the request, executed and posted the result, and then you can just write back the result. You can have timeouts in place. I talked about timeouts in this channel as well. I have a new video coming up about timeouts, right? So much content coming in, guys. So yeah, CPU. And the final use case is when you have a large volume of predictably small tasks. So you're executing the same task over and over and over and over and over again, many times, right? Thousands of times, 10,000s, 20,000s of times. Right? And that tiny task, that single process is serially executing these, right? Just serially going through this tiny, predictable execution. In that particular case, right, you can spin up a new thread, right, and then give it that task and then start distributing those tasks. Now, this is like a classic distributed system problem, right? Where you have something, I think that's what people mostly use threads for. You have something coming in, you have a lot of tasks, just let's distribute it on the threads and let them do their work, right? And then let them agree back and then post the results, right? That's what you essentially do. So that's a common use case for using threads, by basically taking that, and then that will increase what we call the throughput, right? If your backend only processes 1,000 requests a second, you can increase that to 10,000 requests per second, theoretically speaking, by making 10 threads, right? Of course, that is not always the case. There are so many other factors. Depends on the request pattern. What does this request do, right? What do we mean by executing the request, really, right? And a common example of this, simple really, is a connection acceptance, right? You have a lot of client. You're a CDN. And one of the hardest thing for a CDN or reverse proxy is to accept connections as fast as possible. You see, when a client connects, how can I accept a connection? Because let me accept and encrypt. Let me do all of this tasks together, right? And when you have one process accepting all this connection, you can do it very fast. But you can only go so far because you're literally serially accepting connections, right? You literally call accept. And the accept is a system call. So there is a little bit of an overhead with that. But you're accepting. So give me the next, I don't know, one connection available. I don't know if you can accept multiple at the same time. That would be nice. I need to look that up because that should be something that is readily available, right? Accept multiple connections at the same time. Like assume it's available in the accept queue, and you just like call accept bulk, and you accept 10 at a time, right? Something like that. If you don't accept connections fast enough, those connections will sit in the what we call the accept queue, right? Because the kernel technically finishes the handshake, right? And it puts the connection handler, if you will, or the FD. There is no file descriptor yet. You just put it in something called the connection, the accept queue. So say, I finished a connection. This is ready to be accepted. Once you call accept on this, I'll generate a file descriptor, and I'll give you a pointer, and I'll update your process control block, and I'll tell you all about this information. I'll create the receive buffer and the accept and the send buffer for the connection and all that stuff. I'll do all of that for you, right? But you have to call accept. Okay? So if you don't call accept fast enough, you will risk filling up the accept queue, and you will risk timing out clients from connecting to your backend. As a result, when they do a send ACK, the kernel, the backend kernel, will never reply back with a send ACK at all. We'll just sit there. I just no, I can't. I don't have a space. Sorry. So we'll just leave that. So what you would do is you would spin up multiple threads, and all of these threads call accept in parallel. Accept. So they all just fight to accept connections. Like, all right, this way you accelerated that. Now this is where the problem of threads come into the picture. Well, the moment you have multiple threads working and competing on a shared resource, especially if that's shared resource within the main process, then you have locking going on, right? Especially in this particular case, in the accept case, there is something called the accept mutex, where there is only a single queue, right? No two threads can call accept at the literal same time, right? So they'll have to acquire a mutex, and I talk about mutex in my course. This is just a locking mechanism to ensure serializability between threads, right? And safety as a result, and you don't get race conditions. So you have one queue and everybody's fighting in that. So you get other problems with threads in this case, right? That's where threads become really dangerous. Especially if you want to debug this thing, forget about it. Debugging multiple thread application, oh my god. That's where you need to really more understand what's going on as opposed to actually debug it. Right? So one solution to this particular unique problem is to share. It's called something called port or socket sharding with a D, not a T. Okay, sharding, right? You shard a port, okay, and then as a result, what you would do is, hey, you can have multiple threads listen, if you will, on the same socket port address IP, and as a result they will get their own listener socket, but they all the same IP address and port, right? Using SO reuse port. This way, if they all call accept, they will be having their own accept queue, so there is no contention, right? As a result, and the kernel will take care of distributing connections between these queues, right? So that's just a little bit of internal knowledge for you there. But yeah, keep in mind, threads comes with problems, right? But these are the few cases that I know of where they can be really useful to be applied, right? Have you used threads before? Have you had nightmares using threads? Let me know. And I'm going to see you in the next one. Take care.